Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos.
Anyways, today in this particular lecture, we're going to discuss about the demodulation of your traditional AM signal. So here we're going to discuss two widely used methods such as your square law detector or demodulator as well as your envelope detector. So these are the outlines. We're going to start up with the introduction. Then we're going to discuss about your AM signal detection methods one by one. That is your square law detector and your envelope detector. Then we're going to discuss about the various advantages of your diode detector circuitry, such as its simplicity and easy implementation. And finally, we're going to conclude by discussing some of the limitations of your diode detector circuitry, or you could say your envelope detector. So in our last lecture, we have discussed about the generation methods of your AM signals, such as your square law modulator and your switching modulator with the help of your nonlinear device. And in your switching modulator, we are using some diode as your ideal switch circuitry. So in this particular lecture, we will focus on how to detect your generated AM signal, or you could say simply how we will going to demodulate our AM signal. Now we're going to discuss demodulation of AM wave. So what is demodulation or detection? So the process of extracting the message signal back from the modulated waveform is termed as the demodulation or detection. Obviously, if at the transmitting side we will going to modulate our signal, then in order to obtain the actual information signal at the receiving side, we have to perform certain demodulation operation. Then only we are in a state to effectively find out the actual information signal. So there are various ways to measure or detect the amplitude of the waveform. Here we are more focused about the amplitude of the waveform just because all the information must have been contained in your amplitude only. So the two methods that are widely used for your detection or demodulation of your amplitude modulated waveform are your square law detector and envelope detector. So now we're going to take up one by one. So square law detector. So this particular figure is basically showing the block diagram structure of your square law detector. At input side, we'll be having your ST, which is nothing but your amplitude modulated waveform. That signal would have been applied to your nonlinear device. So it could be your any nonlinear device which is basically operating in your nonlinear region. So it could be your diode or transistor or any nonlinear device. So then after this the outcome of your nonlinear device would have been passed through your low pass filter. So via appropriate filtering we will going to get this message signal or your demodulated output. So how we will going to obtain our actual message signal? Via appropriate filtering, we have to look some mathematical details. So a square law detector can be obtained by your square law modulator, as we have already discussed, and your nonlinear device can be of anything, likewise your diode or transistor. I mean any device which is having some nonlinear characteristics would have been used instead of your nonlinear device. So let us say that the nonlinear device have the transfer characteristics as V2T is equal to A1 V1T plus A2 V1 square T. So here this is the simple input output relationship for any nonlinear circuits. So here V2 is your output and V1 is your input signal. So when we're going to apply input signal V1T as the input of your nonlinear device, the output we will going to obtain is your V2T, and the relationship that we have in your input and output is your nonlinear. So this square term is basically representing nonlinearity, and this A1 V1T is basically representing its linear characteristics. So we know that the input to the nonlinear device is the AM signal, which is given as, so modulated signal can be given as your AC times of 1 plus mu times of mt cos of 2 pi fct, where this mu is basically showing the modulation index of your AM signal, AC is the peak amplitude of your carrier signal, and fc is your linear carrier frequency. So this signal ST is basically the input to your nonlinear device, which is nothing but your modulated signal. So now the output of the signal may be calculated as, so what we have done is here we just simply have put this value of V1T in this particular equation, and what we obtained is V2T will be equal to A1 times of AC of 1 plus mu mt cos of 2 pi fct plus 1 upon 2 A2 AC square times of 1 plus twice of mu mt plus mu square m square t multiplied with your 1 plus cos of 4 pi fct. So here we just simply have put this value of st in this particular equation, and we have collected various components of your signal. So now the desired frequency signal, or you could say your message signal, that is analogous to your A2 times of AC square mu mt. This is nothing but your message part, and this is, if you are talking about, these are your some multiplying constant. So if by anyhow we are in a state to evaluate this particular term, then we can extract the message signal, and this would have been done via passing that particular signal that we have obtained in our last slide via passing this through a low pass filter. So if we will going to pass that particular signal through our low pass filter, whose carrier frequency, or you could say whose critical frequency is your FMT, could serve the purpose to obtain our message signal. This method gives the better result if the value of the modulation index is very small, else distortion will be larger. Obviously, if the modulation index is much higher, then in that particular case, the distorted waveform we will going to obtain, or we could say that the quality of signal will be inferior. So this is how, with the help of a square law detector, we can demodulate our signal or extract our signal. So now we will going to discuss another method of extracting our message signal from AM modulated waveform. So this is the block diagram structure of your envelope detector. Here we'll be having this diode circuitry, a capacitor, a bleeder resistor, and low pass filter, and this is your coupling capacitor. How this particular circuit will going to get functional, let us discuss. So initially we're going to apply our modulated waveform or amplitude modulated signal to your diode circuitry, and here diode is simply going to work as your half wave rectifier. So how this particular circuit will going to functional is, so diode will be conducting our modulated waveform when the amplitude of this modulated waveform is greater than 0.7, or ideally you could say is greater than 0. For the positive half cycles of the envelope, our diode will going to conduct, and when diode will going to conduct, this particular capacitor will going to charge up to that potential. And in the negative half cycle, when diode is in non-conducting state, since the potential of capacitor is much larger, so that capacitor will going to start discharging through this bleeder resistance R, and that output we will going to obtain from this particular circuitry is passed through your low pass filter, which would have been tuned through your message signal frequency, or you could say your FM. So we will going to obtain our message signal, and this coupling capacitor would have been used to block all the DC component. So here at the output we will going to have our message signal. So this circuit is essentially just a half wave rectifier, as we have discussed that diode operation. That diode is simply going to act as your conducting and non-conducting state. That is, for positive half cycles it will going to conduct, and for negative half cycles it will not going to conduct. So which charges the capacitor to a voltage, to the peak voltage of the incoming AM waveform. And now what will going to happen? When the input wave's amplitude increases, the capacitor voltage is increased via the rectifying diode. Obviously this is the charging of your capacitor. That is, capacitor will going to charge instantaneously to the instantaneous value or voltage of your envelope. So when the input's amplitude falls, the capacitor voltage is reduced by being discharged by the bleed resistor R. This is what we have discussed. That is, in your negative half cycle, when the capacitor's voltage is greater, then in that particular case your capacitor will going to start discharging through that bleeder resistor R. The main advantage of this form of amplitude modulator is it is very simple and cheap. Since we have discussed its circuit component, so it is only being containing your diode, resistor, capacitor, and your low pass filter. So due to its simplicity, it is widely being used. So that is why it is used so often, that we have discussed. However, it does suffer from some practical problems that we're going to discuss later. What are the problems associated in your envelope detector? But first of all, let us discuss important parameter, that is time constant of the capacitor and how it will going to affect our signal detection. So this particular figure is basically showing your envelope detector outcome. So if we closely observe that this particular waveform is basically showing your amplitude modulated waveform. For the positive half cycle, we are only being discussed about when we're going to pass our this AM modulated waveform through your diode, we will only going to have this positive part. that is for your negative cycle, it will not going to happen just because diode is in your non-conducting region. So as we have mentioned that when we're going to pass our envelope through your diode, diode will going to instantaneously charge the capacitor C. So for the negative half cycle, when diode is in your non-conducting region, that is I'm talking about from this particular cycle, that is from this particular duration, our capacitor will going to discharge. Or we could say that when the capacitor voltage is larger than your incoming envelope signal, capacitor will going to start discharging through that resistor, or you could say your bleeding resistor R. So this is your discharging cycle. Then again when diode start conducting, it will again going to charge, then again discharge, again charge and discharge. So we are getting this sawtooth sort of waveform as the outcome of your envelope detector. So here the important point that we have to discuss over here is what will be the value of your time constant so that we can get the appropriate outcome at your envelope detector, or we are in a state to get the actual message signal through this detector circuitry. So as we know that the time constant tau is equal to RC will going to play an important role, and it will going to gives us the information about the charging time as well as the discharging time. So if the time constant tau is equal to RC is too large, then what will going to happen? And if time constant is quite low, then what will going to happen? We need to discuss that. So what is our requirement? We just simply wanted that our capacitor should be instantaneously charged to the incoming voltage so that it can model the actual signal variation, and discharging time should be higher, just because if discharging time is very low, then in that particular case we will going to have lots of ripples. Suppose if discharging time is very low, then instantaneously our capacitor will going to discharge from this particular point to this particular point. Then again if discharging point is too low, then again in the next negative half cycle of your carrier signal, our capacitor will going to soon discharge. So if the discharging time is too lower, then in that particular case we will going to obtain higher number of ripples, which is undesirable. What we can say is, so it is good that RC, or you could say your time constant, is much larger. So this particular figure is also showing that too large value of RC or time constant is also not desirable. Why is it so? Just because if time constant RC is quite larger, then what will going to happen is our capacitor will going to take larger amount of time to charge or to approximate that incoming signal voltage, and it is also going to take much larger amount of time to discharge. And if RC is too large, then obviously for dynamic signal variation our capacitor will not going to replicate the actual signal variation. This particular point is showing that particular thing, that what I want to explain is, if time constant is too large, then at this particular position if capacitor would have been charged, then if in the next cycle capacitor has already been charged up to this potential, fine. And if time constant is too large, then it means capacitor will going to take larger amount of time to discharge its voltage. So obviously these particular are these points, at these particular points your capacitor voltage is much larger in comparison to your incoming signal. So obviously capacitor will going to fail to approximate the actual signal variation, and if this is the case, our detector circuitry will not going to functional well. Conversely, we could say that the time constant value, that is tau is equal to RC, must have an optimum value so that it is in a state to approximate the signal variation properly. That is, your time constant value should not be too low or should not be too large. If it is too low, then ripples will be higher, and if it is too high, then it will going to fail to approximate our signal variation, and we are not in a state to extract our actual message signal back. So we have to have some optimum value of your time constant tau is equal to RC. So effect of time constant, although I have already discussed, but still let us formulate whatever we have studied. So the operation of the circuit requires careful selection of T is equal to RC. So here we have mentioned this T as a time constant, but I have while explaining I have used this particular term tau. So it is conversely would have been used in several textbooks, that is tau, and T is representing your time. So here just consider that T is equal to RC is basically showing your time constant value. So if RC is too large, discharging will be slow and the circuit cannot follow the decreasing envelope. This is what I have discussed in your previous slide. That is, if RC is too large, then the discharging of the capacitor will be too slow, or you could say that our circuit will going to fail to approximate the signal variation, or at the output of detector we are not in a state to get the exact input signal or exact information signal. So when the RC is too small, this is the another case, the ripples will be high. Why is it so? We had already discussed. So the ripples are finally removed by your low pass filter, since this appropriate filtering would have been used to smoothen out our waveform, which will going to further reduce out the value of ripple. Ripple is nothing but this is the alteration or signal variation. So the DC value is blocked by the coupling capacitor CC, as we have shown in your blocks diagram structure. So now we're going to discuss the advantages of your diode detector. So first advantage is its simplicity. As we had already discussed that diode detector is very simple and easy to construct, as the circuit components are lower in number as well as they are readily available. Since it is consists of only a diode, a low pass filter, a capacitor and a resistor. So that is why we are saying that it is very simple to construct. The circuit is very straightforward, consisting of a very few components. This is what we have already discussed. So now second important point or advantage of a diode detector is your low cost. So since it is requiring fewer number of components, and the fact that components are not specialized, that is, I mean, they are very genuine, very simplistic components such as your diode, low pass filter, capacitor and the resistor. From this form of detector is very cheap. That is why it is widely being used in your AM domestic radios. Obviously here we are not at all commenting over the quality of the reception, but still it is quite cheaper since it is using very basic components. Then another advantage of your diode detector is your asynchronous detector. That is, this detector does not depend upon the frequency and the phase of the carrier at the receiver. That is, we wouldn't require some synchronous detection method in order to detect our signal with the help of your envelope detector. About your synchronous detection, we have already discussed that at the receiving side also, for generating local carrier frequency, we will be requiring the information about your transmitted carrier signal. So here this is not the case, or here this is not the requirement. So now we're going to discuss the limitation of diode detector. So what are they? So the input to the detector must be band pass filter around the desired signal, or else the detector will simultaneously demodulate several signals. Why is it so? We had already discussed that the signal we have received, it is going to contain multiple high frequency component also. So if we not going to perform effective filtering, then we will going to get several different components which will further going to distort our signal, or we are not in a state to obtain our message signal effectively. So filtering can be done with a tunable filter, or more practically a super heterodyne receiver. So super heterodyne receiver is a specialized receiver which uses a tunable frequency and can effectively reconstruct our message signal. So it is basically using your intermediate frequency concept. So how super heterodyne receiver will going to get functional, we'll going to discuss in our upcoming lectures. So as of now, we could only understand it as super heterodyne receiver can effectively detect several AM signals which are being transmitting over different frequency ranges. So if the signal is over modulated, distortion will occur. Obviously for over modulation case, we have already discussed that here your modulation index MA, or you could say your mu, is greater than 1. So 180-degree phase reversal would be there. So some of the message part we will going to miss since we are using your diode circuitry. What basically I want to mention over here is, if we are using this diode detector circuitry and if our AM signal is your over modulated, then in that particular case we are not in a state to obtain that signal value which lies below the conducting voltage of your diode. So obviously if some message will going to lie over there, we will definitely going to lose that particular information. And if we're going to lose certain amount of information, then obviously distortion will occur, or we could say that we are not in a state to obtain the actual information signal back. So most of these drawbacks are relatively minor and are usually acceptable trade-offs for the simplicity and the low cost of using an envelope detector. So obviously these drawbacks are quite minor. If we are not at all overly cautious about the quality of the signal reception, then we can make a certain acceptable trade-off, and simplicity is the major plus point of this particular diode detector circuitry, along with its low cost. So that is why it has been widely used. So hopefully you guys have got certain idea about your square law detector along with your envelope detector. In case of any doubt, you can ask me in the comment section. I'll try to solve them out as soon as possible. So these are the references that has been used to prepare the slides. Thank you very much for your patient hearing.